Hello, everyone. Welcome to today's webcast on how to put new profit in old products with SOLIDWORKS simulation and plastics. I'm the moderator, Krista Prokos. Before we get started, I want to let you know that you can submit questions for today's presenter by typing them into the Q&A panel at any time. We'll collect them and address them at the end of the presentation. Now, I'd like to introduce our presenter. We're happy to have with us today Nathan Sneller. Nathan is an application engineer at Fisher Unitech and our ambassador of simulation. Nathan, take it away.
Good morning, everyone, and thank you, Krista. First of all, I want to thank you for joining in. I hope we have a few minutes of fun today. The title, as Krista said, is Putting New Profit in Old Products with SOLIDWORKS Simulations and Plastics. We're going to focus mainly on taking out screws and fasteners and hardware, and if we get time, we might look at a flat spring as well. But this is really my favorite part of engineering. Just a little bit about me. I've been using SOLIDWORKS, looks like I said, since 2004 here, and I've been teaching it at a community college since 2009. So I've been pretty into it for a while. The last 10 years, I ran an engineering firm that specialized in mechatronics, basically, and we did a lot of electronics enclosures as well as plastic part design. And my role here is the ambassador of simulation, spreading the good news. But then I also have a pretty extensive product development background, so I'm a resource available to all of our customers and partners. If you need an extra set of eyes or ears to bounce something off, feel free to contact me at any time. That's why I'm here. As you can see, I've got a inexpensive tape measure that can be purchased at Harbor Freight for $16.99 and less if you have a coupon. I think it's more on holidays. If you buy a lot of tools, I think there's a lot of debate whether or not Harbor Freight is the place to go, but that's not the conversation topic for today. Why I bought one of these things, oh my goodness, 15 years ago now, right after college but before I had a job, is it really struck me as a part that was just ripe for some design for manufacture, value enhancements, we'll call them. And I bought it, and it sat in my garage for years, and I measured a couple of things, but this just seemed like the time and place to bring it up, so I'm excited to get into it. As you can see here, it's a $17 part, but if you swing over to Alibaba, Harbor Freight is probably paying between $1 and $2, and if they're buying it shipping included for $2 and they're selling it for $16, that's 400, 500, 600% depending on what values you use. So it's a huge markup for Harbor Freight, and they're probably not interested in cutting a couple of screws out. But the company in China making it, or if there's a US company that makes it overseas, is selling it for $1 to $2, and they have what I counted as 8 extra screws, 8 extra nuts, I guess 2 more screws, a flat washer, a whole bunch of stuff. I should probably just not list it, but jump over to the next slide here. So on the top half, I've got the list of parts that we got to keep, and on the bottom, the list of parts that we're going to get rid of. So 21 parts in all are going out the window. You can see I've broken it down here, and like I said, the most time consuming was the screws. I'm sure it takes just about as long, probably a little longer to put them in than it did to take them out. And then we've also got a couple of other screws. One holds the little hub here. I guess you can't see my pointer. Holds the hub in place with this washer, and the other screw holds this little knob on there. So then my updated design has none of those screws. Still has a couple rollers, but for the most part, it's all plastic. So the first topic is, well, how do you do it, Nate? And screws have got to go. So this design was actually a little DFM'd to begin with. You can kind of see that the screw is in a hexagon hole at the top and a hexagon at the bottom. The bottom hex holds the nut quite well. The top one is large enough such that the screw fits in there, and nobody has to reach through and hold that nut in place with a wrench or anything. And the way it's set up, it's a mirror image, so the same plastic piece is used for A and B. But my design on the left reduces 8 screws, and I think I figured about a minute of assembly time. Maybe in the future I can do a webinar where we actually build this thing, 3D print it, and do a time trial for assembly. So just some notes from a product development standpoint. A 30% lead-in usually works quite well for these things. And then where minimum angle is called out over here, that really highly influences your separation force. When I originally ran this, I had 10 degrees, and it really didn't stay together at all. And now you'll see my new force, but I've decreased it to 2 degrees. Now, if you can find a way to make that inverted, it won't come apart until you rip it apart. So take that for what it's worth. And then you'll notice I have the ample clearance area, of course, and that's just an indication to make sure that the part will actually fit through the hole. I've had difficulties with that before. Just maybe it's a little too tight, or you're expecting it to compress more than it does. And then as an engineer, there's always some unfinished work. Now I just copied the clearance between the ID and the OD here, but there's room to bring it up and make a little bushing surface if you have time, just a solid material. So things to talk about. Now how I sized the snaps in order to make sure it fit was I made a slot with the same radius as the arms, or what was the pin before, and then did an extrude cut on that little conical shape. And what that allows is that when you close it up and those two endpoints touch, it's now the same diameter as it would be if it were just a solid piece, so you'll know it'll fit through. Now, of course, you want to see that it works, or how it works. So I'm going to switch over to SolidWorks here a minute, I think. So on my screen, this is the original with the nuts in it. And let's pop over to my demo piece here. Now, the key to FEA and to making it work for you and fast enough to be viable is to simplify. So we could cut this part in half because it's symmetric, but we could also just cut off this little bit here because we're only looking at the snap features. And then to simplify it even more, I really only need to look at one because the other one's the same. I've got 10 snap features in here, so we're just going to break it all the way down to one. Now I drew a sketch on here just to get half of this. And if you're unfamiliar with this feature, it's really kind of handy for things like this. Under Insert Assembly Feature, there is a cut. So if you didn't know, you can actually add a few features within an assembly. What this does is starts with both pieces. I'm going to go through all cut in both directions and just flip the side to cut. So that should just leave this little area here in both directions. And now I'm left with this little sample. Now the interesting thing is if I open this part up, everything is still here. It's not a feature within the part, it's only a feature within the assembly. So the first step that I need to do, if you haven't done it already, is open up simulation, or do the add-in for simulation, which if I have my add-ins, I don't have that turned on, do I? The add-in menu is right there, turn on simulation. So in simulation, I can make a new study. And because this is plastic and it has a large sliding contact, I need to use a nonlinear simulation, and I'll use static. Now, available with SolidWorks, when you're on subscription, I think it goes away when you're not, is an expanded material database. This is quite handy because the original database has some things, but say for plastics, when I get down here to polypropylene, I just have a generic PP copolymer. It doesn't mean a whole lot to me, probably not to you either. So I can click here, and I'll tell it not to give me the warning again. It's popping it up on a different screen. Hold on a second. So So I can select my study type as nonlinear. I want a linear, elastic, isotropic material. It's a plastic, and I know I'm looking for a polypropylene. It's about the cheapest plastic you can buy. And if you're making a tape measure for $1 in China, that's probably what you're going to want to go with. Now I can select from any of these 4 databases. I just use the first one for default. And then here it lists a polypropylene, a few of them, gives a number for it and everything. You just download it and add it in. In the interest of time, I'm just going to use the one that I already downloaded. So I'll apply the material and make sure I set that to linear elastic. From here, it's a matter of applying the contacts. That's really the only thing we're solving for here. So I want to change this from bonded, which means they can't go anywhere, to allow penetration. And then I'm just going to add a second contact set for no penetration. And that means that any faces in the first group cannot penetrate faces in the second group. So it makes a lot of sense, really. Seems intuitive, right? And for some reason, I'm doing this the hard way. If I just hit select tangency, it'll grab all of them. And now I looked up the coefficient of friction for polypropylene, and it was about 0.44 for dynamic and 0.76 for static. Now in this study, I want to check that we don't develop too much stress and break the snap as it goes in, but I also want to make sure we have sufficient retention force. So that retention force is going to depend almost entirely on the static friction. So I'm just going to set it to 0.76. If I needed to do it the other way, I'd do it in 2 separate studies, but we're just doing one right now. And now, because I cut it in half, we need to add a symmetry feature. So that's under Advanced Fixtures and Symmetry. Just click one face, usually. Come on. There we go, Symmetry. Had the wrong one selected there. And now I just want this to be able to move up and down, not left to right, so I'm going to add roller sliders, which essentially just allows these things to slide around on those faces, but not to come off of them. And then finally, I believe finally anyway, I need to fix the bottom face. So I need something to press against. And now I can apply a load, but in this case, I'm not really, I want to see what the forces are. I don't want to specify what forces are applied. So I can choose prescribed displacement. This actually shows up as a fixture. So I'm going to use the reference geometry, and I'll put it on this top face and give it a direction of the top plane. And I measured before, and it's about 0.56 inches down. And then this variation with time, that's another thing you get to do with nonlinear. I'm going to change from just a straight line to a curve. So it says at 1 second, or basically 1 time step, it's going to go to 1 times 0.56. I'm going to reduce this to 0.9. So the last 10% of my study, from 0.9 to 10, 0.9 to 1 rather, I'm just going to pull it back out so I can get that retention force, see what it takes to get it to come back out. And now I believe I also added a mesh refinement. So apply a mesh control, and just like I did before, I'm going to do a select tangency here to get all the faces, select tangency here to get all the faces. You need to remember to get these bottom faces and these guys here. So what this does, I'm going to make it finer in the areas that I care about and leave it good and coarse in the areas I don't. And let's run the mesh. Should only take a second or two, I hope. And there you can see that way on the outside, there are these big, nasty not very accurate elements, but we don't care about that. And on the faces that do matter, we have nice small elements. You want to have 2 elements through the thickness. Sometimes it's confusing. This is 2 elements, not 4 elements. You could count 1, 2, 3, 4, but it's not really what they mean. You want to have at least 1 element that's not touching the other side. So that looks like a good mesh, good enough mesh. And now to save time, I'm going to switch over to one that I already ran. And now for everybody's favorite part, we get to watch it move. So you see it goes in and it comes back out, and our stresses are nowhere near yield. So that's a win. It looks like we have a few areas down here that maybe are in the we should think about it range, but nothing critical. It's just on the very tips there. So that's good. And then in order to look at the extraction force, I'm going to right-click here and do List Result Force. And I need to give it a direction. At least it's easier if I give it a direction. Come on, you can do it. There we go. And then I'm going to look at my time of about 0.9 because I knew that's where it settled in and I started to pull back on it. So 0.1, check the next one. It's actually sliding a little bit here. And this is my maximum, is at step 20. So it's almost 1/4 pound of force to pull that apart. So multiply that by 10. That's what, 2.5 pounds of retention force, so not too bad. It's going to take a little bit of pulling to get it apart. That's the main thing. So let's jump back into my PowerPoint here, if we can. Where'd it go? There we go. All right. So here you can see the stresses are, this is a stress plot over the whole thing, are very much below our yield, so that's good. Our insertion force is not very much, 0.68 pounds. And here's that video from before. I've adjusted the strain just to show what areas strain the most. And then here you can see, looks like I had a decimal error in one of these two, but retention force is quite high. We don't have to worry about that coming apart. Oh, I did the demo in SOLIDWORKS already. Now the other part that might be interesting to look at, and if you want to see in more detail, you can contact me and I'll talk you through it one-on-one. But this was kind of my favorite part in the whole thing. Let's get it open again. The other model, the original model, oops. Has a pin that holds this piece in place and then a flat spring that tensions the crank arm. Now this design here has a plastic piece, little nub that sticks out. You're able to drop it in here, slide it up over the integrated plastic spring, and then it has a couple of detents to hold it in position. So that's best. Here we go. Oops, wrong button. Come on. So just a video, a little choppy of it going in, but it shows the idea. It snaps in through there and holds in place. Now the next question is, we've designed it, now can we make it fill? And the first step here was to run the default plastic with all the default settings, and as you can see, as it gets out there, it stops. So that's a short shot. We did something wrong. Oops. So what I did, let's bring up SOLIDWORKS again on that one, and that is plastic frame snap. is I took a look at the material temperatures. So I'm going to open the database of my polymer. I was just using the generic polypropylene for this one. Oh, it's on the wrong screen again. And under polymer material, I can see that I can raise my temperature from 446 all the way up to 536. So actually in this one, I ran it at 500 degrees. And we'll flip back over here. And so at a 500 degree temperature, it fills all the way through and we're good to go. So it wasn't an actual emergency, it was just a processing tweak that we had to do. So if I sent this to my Chinese molder, I could say, I want you to run this polymer and I want you to run it at 500 degrees and it should fill without any issues. I've had issues before with having to coach them through what settings I want and what materials and all of that. But it's nice to know ahead of time so you can avoid those delays, because you always lose a day, almost two, dealing with China. At least that's been my experience. So that wraps up what I have to show